All right, so this is the beginning of our brief calculus class. For what it's worth, my name is John Grima, and when you see me around, you can more than definitely call me John if you care to. If you feel that's not appropriate, you can call me Mr. Grima. That's completely fine. I want to spend a few minutes talking about what calculus is, but not a lot of minutes. And I've done this video a few times trying to condense what calculus is into a manageable bit of time, like 5 minutes. And I keep getting up to like 30 and 40 minutes, and my lectures aren't terribly informative or that good. So I'm going to hold off on just giving a big global explanation of what calculus is. And I'll kind of, as we get into the course and we start getting into stuff where calculus is used, throughout the course, I'll explain what calculus is, what it's used for, in little 2 and 3 minute increments through my videos. That way you don't have to sit through 40 minutes all at once. You'll get maybe 20 different 2-minute blurbs on what calculus is. For what it's worth, it's about 400 years old now, calculus. Calculus was invented independently by two mathematicians or scientists. Sir Isaac Newton, the guy that the apple fell on his head, invented it, and first, and I think it was in about 1665. Newton's theory is exactly perfect. His notation is a lot different than what we use now. And then a second mathematician / scientist, I don't know if I could spell his name, invented calculus without knowing that Newton did it about 10 years later. And Leibniz's his notation is more like the notation that we're going to use in our class. So each video is going to contain a section or a part of a section. Some of my lectures get kind of long, and I'll break the video into 2 sections. If there's some underlying theory that needs to be explained before we start a section, then I'll do that right up front in a video. If I think I could mix the theory of the section in while I'm doing problems, then that's what I'm going to do. Guaranteed, in every video, I'm going to do as many of the even numbered problems in a section that I can fit in a reasonable amount of time. And then your homework in every section is going to be to do all the odd numbered problems in a section. I'll structure the videos so that after I do an even numbered problem, I will put on the screen an odd numbered problem that has the same skill set. And if you pause the video, you can do the odd number problem that's flashed up on the screen, and then go to my webpage and check your answers. I'll show you in class where to check your answers. I can't show you now because this camera isn't connected to the internet, so I can't show you my website. So I'm just going to jump right into section 1.1. And the first even numbered problem is problem number 2. And the first 3 parts of this question aren't calculus questions at all. They're kind of Math 092 beginning algebra questions. Each one of these questions refers to the graph of the function that I called f of x. And each one of these questions has a function notation and a number in a parentheses. Anytime you see the function letter, like f, with a number in a parentheses, that number in the parentheses stands for an x value, and it's asking me to give the corresponding y value. So for part A, the one that it gives me is x equal to 1. That's this one right here. So that one is the one on the x-axis, and I'm supposed to scan above that one on the x-axis and find the point on the graph that has 1 as its x-coordinate, and the answer to my question is going to be the y-coordinate of that point. Because this is functions, there can only be one point above each value of x, otherwise it wouldn't be a function. If you had 2 values or 2 points above a single x value, then it wouldn't be a function. So as I look above 1, I see this open circle and I see a closed circle. Open circles aren't considered points on the graph, but closed circles are. So this is the point that 1a is calling out, and that point is the point 1, 1. So f of 1 is the y value of the point that has 1 as its x value, and that y value is 1. So my answer to question A is going to be f of 1 equals to 1. For part B, the 3 that's in the bracket is calling out that 3 on the x-axis, and I'm going to go up to the graph. I'm going to find the point on the graph that has 3 as its x-coordinate. That's this point right here. That's marked real nicely for me. And the answer to question 2 is the y-coordinate of that point, and that's going to be 2, because that's the point 3, 2. So for my answer, it would be nice to say f of 3 equals 2, not 3. So for your answer to part B, if this was a test question, the best answer would be to say f of 3 equals to 2. An okay answer, and it's probably the answer I'd actually have on my key, would be if you just wrote the number 2. So you don't necessarily need to write the problem with the answer or with the y-coordinate. But it's better, but it's not a deal breaker if you don't. And then the last part, f of 2, I had this handwritten in because I changed the problem. Doesn't matter to you. The 2 that it's calling out is that 2. I go up and I look for the point on the graph that has 2 as its x-coordinate. Open circles aren't points on the graph. Closed circles are points on the graph. So that's the point 2, 2. And in each of the parts A, B, and C, I'm looking for a point on the graph and its y-coordinate. And so the answer for part C is going to be f of 2 equals to 2 as well. That's not calculus, that's just basic algebra. The rest of the parts of number 2 are going to get into calculus. And real specifically, I see a notation that you probably have never seen before unless you took calculus at some point. The word LIM is short for limit. And just like the parts A, B, and C, parts D, E, and F of number 2 are also looking for the y-coordinate of a point. So a limit, it asks me to find a y-coordinate, just like the questions A, B, and C wanted me to do. One of the differences between parts A, B, and C and these 3 that are up here now is it asks me to find a y-coordinate, and the point doesn't necessarily have to be part of the graph. It could be one of the y-coordinates of an open circle. It kind of depends how the problem is written. Unlike A, B, and C, they specifically are only calling out points that have closed circles. Limits can take the y-coordinates of points that have open circles. So when I look at problem D, I read this as the limit, let me just write over here, the limit of the function f of x, which that's how I read it, but I think of this as the y value of the function f of x as I approach on the graph x equal to 1. That's the 1 right here. And the little exponent that has a negative means from as I approach x equals 1 from the left side. This is kind of the heart of calculus. Limits are integral in doing calculus problems. So if I looked at my graph, there's this is the x equal 1 that we're calling out. And to the left of this dotted line, I would say that's the left side of x equal 1. And to the right of this dotted line is going to be the right side of x equal to 1. Isn't it hardly? I mean, it seems kind of obvious. So what the limit wants me to do, to find a limit, what I'm supposed to do is I'm supposed to trace, for this limit, my trace on the graph from the left side of x equal to 1, make little arrows. And those little arrows are going to point to a point, which might have an open circle, it might be a closed circle, actually might just even be part of a line. And the y-coordinate of the point that I'm pointing to is what the limit is. This point right here, it's an open circle, is the point 1, 0. And I would say the limit as x approaches 1 from the left side of the function f of x is 0. So a limit wants me to find a y value of a point on the graph. And it's telling me what the x coordinate is. For part E, this question right here, again, it says find the limit, or find the y value, which is the same thing as finding a limit in this case, of the function f of x. So this is what E is wanting me to find. As I approach x equal to 1 on the graph, so I'm tracing on the graph from the right side. So what I'll do is I'll get to the right side of the graph and I'll start tracing. It doesn't matter where I start tracing, but it matters where I stop. And I'm going to stop right before the little dashed line that I drew, because that's the line that goes through x equal to 1, and it's pointing towards a point. That's the point 1, 1, and the limit is the y-coordinate of the point that I'm approaching. So the answer to part E, the limit as x approaches 1 from the right side of the function f of x, is 1. So parts D and E are called one-sided limits, because to find the answer to part D, I only traced on the left side of 1. To find the limit in part E, I only traced on the right side of 1. Part F is considered a two-sided limit. And a two-sided limit is a number if the left and the right sided limit are the same number. So had parts D and E both had the same limit, that would be what the answer to part F is. If parts D and E, if the left-hand limit and the right-hand limit aren't the same, then the two-sided limit, the limit without a little exponent, doesn't exist. So for part F, a two-sided limit either doesn't exist I'll write D and E for does not exist, or it equals the left limit and the right limit when they're the same. So for part C, or for part F, I look at D and E. If D and E are the same number, if the left-hand limit and the right-hand limit are the same, then the two-sided limit would be that number. If the left-hand limit and the right-hand limit are different numbers, then we say the two-sided limit doesn't exist. And so the answer to part F is going to be the two-sided limit doesn't exist. We'll do lots of these so you'll get hopefully good at them quickly. So I'm going to move on to do the rest of number 2, which was parts G, H, and I. And then part G, when I look at it, it says find the limit of the function f of x as we approach 3. So I need to find x equal to 3. And this is x equal to 3. and I need to approach it from the left-hand side. So I'm going to start tracing on my graph. Doesn't matter where I start, but I need to stop right before the point that has an x-coordinate of 3. That's the point 3, 2. And the left-hand limit is the y-coordinate of the point that I'm pointing at, and that's the point 3, 2, so the y-coordinate is 2. So when I have that little negative exponent after the number, that means I'm tracing on the left side of the function towards the point and finding its y value. When I have the plus sign with the number, then I'm tracing on the right side of the graph, the part of the graph to the right of that value. So for h, I'm going to trace on the right-hand side, stop right before I get to that point. It's pointing towards the same point. The y-coordinate of that point is still 2, so the right-hand limit again is 2. So the one-sided left-hand limit is 2, the one-sided right-hand limit is 2. If the left and the right-hand limit are the same numbers, then the limit without the little exponent, that's called the two-sided limit, is that same number. If those numbers are different, if the left-hand limit doesn't equal the right-hand limit, then the two-sided limit doesn't exist. If the left-hand limit equals the right-hand limit, then the two-sided limit is that number. So there's a reasonable chance that you can now do all the parts of number 1 and possibly even all the parts of number 3. So what I'd like you to do is pause the video, try to do all the parts of question 1, and then go to my webpage, go to the answers link, and check your answers. If you have all the answers right, then you can move on to the next problem. But if you don't have all the answers right, then we need to figure out what's going wrong. It could be that I just have a mistake in my key, or it could be that you're just not understanding something right. If you check your answer and it isn't right, go to my solutions tab. There's a link that says answers that just gives you the answers without any work. And there's a link that says solutions that shows you how I got the answers with work. So if your answers don't check, click on the solutions tab, check to see how I got the answer, and maybe that will help you understand it. If you still can't figure out how to get the right answer, then either come to class with that question and ask me in class how I got the answer, or send me an email and ask me how I got the answer, and I'll try to do my best to type up how I got the answer, or just come visit me in my office. Anytime I'm in my office, I'm never too busy to help. Usually I do most of the work I need for the school year during the summer. So when I'm during the regular semester, I'm just kind of focusing on helping students. Like right now, this is like May the 29th, I think, and I'm not working now. I'm not getting paid or anything today, but this is probably the best way to do these. All right, so there's a reasonable chance, because question 3 is really not any different than question 1, that you might also be able to do it. I'm going to go ahead and do question 4, but you might be able to do questions 1 and 3 without watching me do question 4. If you get question 3 done, don't even watch me do question 4. Just fast forward right through it. You don't need that extra push. But if you're not really getting 1 and 3, then watch me do question 4, and maybe seeing me do the problems again, or a similar problem again, will help you out. So I'm going to start question 4. Parts A, B, and C want function values, and they only call out closed circle points. So for part A, f of -1, the -1 that's represented in part A is that -1. These little dots here are just to help me understand the graph a little bit better. And I go and I look for a closed circle. I skip the open circle. Open circles are okay for limits, but not for function values. The closed circle that's above -1 on the x-axis represents the point -1, 2. So f of -1 is going to have a value of 2. To do f of 0, I need to find 0 on the x-axis. It's not labeled, but 0 is right there. And I'm going to go on my graph. There aren't any opened or closed circles, but there certainly is a point on the graph. And the point that's on the graph, I can mark it with my own closed circle if I want. I need to know that point's y-coordinate, and that's the point 0, comma 2. So f of 0 is going to be 2 again. The last part, f of 1, the one that it's calling out is the one on the x-axis. I look above the 1 and I skip open circles, move up to closed circles. The closed circle's at the point 1, 3, and so my answer for f of 1 is going to be 3. That's the non-calculus part. Now we'll move on to the calculus part. In about 3 minutes, something horrible might happen with my video because this video recorder will only record for 24 minutes. And at 24 minutes, it starts recording another document. So there might be little hiccups in my videos. And let me know if there are, because I have to piece the pieces together as I do these videos. So part D, the negative 1 here is that negative 1. The negative there, this is the limit as x approaches negative 1 from the left-hand side. That negative is telling me to trace from the left side towards negative 1. So I'm going to get on the graph, I'm going to trace, and I can point to an open circle or I can point to a closed circle. My answer is going to be the y-coordinate of that point, whether it is an open or a closed circle. The point that's pointing to is the point negative 1, 1. So my answer to part D, the limit as x approaches negative 1 from the left side, is going to be positive 1. Part E wants me to trace towards the same negative 1, but start tracing to the right of it. So I started way off to the right. And when I trace to the right, on the right side of negative 1 going towards the point that I'm pointing to, it points to the point negative 1, comma 2. So the y value that it's pointing towards here is 2. And for part F, that's the two-sided limit because it doesn't have a little exponent, it exists if the left and the right-hand limits are the same, or it doesn't exist if the left and the right-hand limits are different. And for part F, I'm going to say it doesn't exist because the left-hand limit is 1 and the right-hand limit is 2. For part question G, I need to find the limit as x approaches 0 from the left side. I'm going to find 0 on the x-axis, and I'm going to trace, and it's going to point to that point. The point that it's pointing towards there is the point 0, 2. So the left-hand limit is the y-coordinate of that point, which is 2. Part H wants me to now start tracing on the right hand to the right of 0 on my graph. And it's pointing towards the same point. So the right-hand limit is also going to be 2. It's the y-coordinate of the point that we're pointing towards. And now for part I, since there isn't an exponent, it's the two-sided limit. If the left and the right-hand limit are equal, the two-sided limit is that value, and that's going to be the case here. All right. I don't know what's going to happen here, but in a second my computer's going to conk out. So for part J, I'm looking for the limit as x approaches 1 from the left, as x approaches 1 from the right side, and the two-sided limit. So let me say that again because I just had the glitch in my video. So for part J, I want to go, so there's a left side of 1, and here's 1, and a right side of 1, and this is the right side. Part J wants me to find the limit as x approaches 1 as I trace from the left side. So I'm going to trace on the graph. My arrows are pointing towards this point. That's the point 0, 2. So the left-hand limit is going to be the y-coordinate of that point, which is 2. For part K, I trace along the graph towards x equal to 1, and the y-coordinate that we go to again is the y-coordinate of that open points. Limits, you're not restricted to only closed points. The answer here is going to be 2 again. And for part L, the two-sided limit, if the left-hand limit with the minus sign and the right-hand limit with the plus sign in the little exponent position are the same number, then the limit without a sign, which is a two-sided limit, is that number. So if these two are the same, the two-sided limit is that number. If these two are different numbers, then the two-sided limit doesn't exist. All right, so I think you probably can do 5, and hopefully you won't have to watch me do 6. So pause the video, try to do question 5, check your answers, and then if you got 5 right, you certainly don't need to watch me do 6. I'll do 6. This could be getting to be overkill, but I never like to undersell, just never like to do too little and leave you not understanding. So part A of number 6, it's a function value, it's only a closed circle. The -2 is this -2 right here. So I go from my graph, look for the closed circle. The closed circle has the coordinates -2, -5. So I'm going to say f of -2 equals -5. For part B, I find 0 on the x-axis. It's not labeled, so I labeled it. I look up and down. I skip that open circle. I take this closed circle. That closed circle is the point 0, -1. So f of 0 is going to be -1. For part C, the 2 that's given is that 2. There aren't any open or closed circles above 2, so I'm just going to go up to the graph. I'm going to put a closed circle on the point where the graph is above 2, and that's the point 2, 1. So I'm going to say f of 2 equals to 1. For part D, it focuses on -2. So this is -2, and this is the part of the graph that's to the left of -2. This is the part of the graph that's to the right of -2. Part D says find the limit as x approaches -2 when I trace on the left-hand side. So I'm going to start tracing. Stop right before I get to the point, and it's okay if it's an open circle point. That point is the point -2, -2, and the left-hand limit is the y-coordinate of the point that it's pointing to. So the answer for part D, the limit as x approaches -2 from the left-hand side, is -2. For part E, I'm going to trace on the graph, start wherever I care to start, doesn't really matter. It only matters where I stop. I'm tracing on the right-hand side of that -2. It's pointing towards the same point. The right-hand limit is the y-coordinate of the point that it's pointing towards, which is -2. And for part F, because the left and the right-hand limit are the same number, the limit in general is that number. So I'm moving a little bit quicker with the idea now a lot of people are probably watching the video right now. For G, calls out 0. So I know for G I need to trace on the graph from the left side of 0. For H I need to trace from the right side of 0. So for part G, the limit as x approaches 0 as I trace from the left-hand side. I start making arrows. Those arrows point to that open circled point. It's okay for a limit to go to an open circled point. That's the point 0, -4. So we say the limit as x approaches 0 from the left-hand side is -4. For part H, the limit as x approaches 0 from the right-hand side, I'm going to start tracing right here. And it still points to the same point, 0, -4. So the limit as x approaches 0 from the right-hand side is the y-coordinate of the point that it points to, and that's also -4. For part I, since the left-hand limit at 0 and the right-hand limit at 0 are the same number, the limit, the two-sided limit, is that number. So the limit as x approaches 0 of the function f of x is negative 4. All right, last three. So I'm calling out 2. So this is x equal to 2. This is the right side of the 2. This is the left side of 2. Part J, find the limit as I trace on the graph from the left side of 2 towards, and then there's not a point marked here. I'm going to stop right before I get to that point, and that's the point 2, 1. So I'm going to say the left-hand limit is 1. For the right-hand limit, I'm going to trace on my graph starting to the right of 2 on the x-axis, tracing along the graph, stop right before I get to that point. That point, its y value is 1, so the right-hand limit is also 1. Because the left-hand limit as x approaches 2 and the right-hand limit as x approaches 2 are both the same number, then the two-sided limit, the limit without the little exponent, is also that number. All right, so now we get to move on to a new concept, limits at infinity. And limits at infinity are still asking me to find a y value. So when I look at the notation in part A, it doesn't have a little exponent positive or negative. This is because positive infinity only has a left side, negative infinity only has a right side. So to do question A, to find the limit as I go off to infinity, well, somewhere off the end of the x-axis is infinity. And what I want to do is I want to trace on my graph and get as close as I can to the infinity. And I did that by extending my graph. So I'm going to trace, 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 trace. And eventually, I can't get to infinity, but eventually I know where the graph is going to kind of bottom out at. And this little dashed line right here, this tells me that the graph, it goes forever and ever and ever and asymptotically approaches that line, which means it gets closer and closer to that line, but it never crosses it or touches it, but it approaches that line. And the y coordinate of this dashed line is, looks like negative 1, huh? Because this is 0, negative 1, negative 2, negative 3, negative 4, negative 5. So the y coordinate of the dashed line that I'm approaching as the graph goes off to positive infinity is negative 1. So I'm going to say the limit as x approaches positive infinity of the graph f of x is negative 1. For the other limit, I'm going to do the tracing towards negative infinity. And negative infinity is at the left edge of the x-axis. So I'm going to trace on my graph. Notice my graph crosses that dashed line and then gets sucked back up to it. The y coordinate of the dashed line is what my limit as I approach negative infinity is going to be. And this line right there, its y coordinate is positive 1 because it's just one tick above the x-axis. So I'm going to say the limit as x approaches negative infinity, which is the far left edge of the x-axis, is positive 1. Your problem 7 is a little bit easier than my problem 8 because it kind of puts the numbers, it's not as cluttered, I think. So you may, with my explanation, be able to do problem 7. So pause the video, try to do problem 7. If you can't do it, watch me do problem 10, and then maybe that'll help you. And if you can't, you can't, and then I'll try to help you out some other way. So I'm going to do problem 10. Part A wants the limit as x approaches positive infinity. So this graph right here, I don't have the dashed line in. Should have put it in like this. So that would be a better version of that graph. And as I trace on this graph the limit as x goes to infinity is the y-coordinate of the dashed line, because this dashed line goes on forever, my graph goes out forever, and the graph, when we have the little dashed lines, it implies the graph doesn't, when we go out towards infinity or negative infinity, the graph gets microscopically close to that dashed line, but doesn't cross it, nor does it touch it. So I'm going to say the limit as x goes to infinity of the function f of x is 2. And then the other side, the graph needs to be extended out to negative infinity, and it's the same deal. As I trace out to get to the far left edge, the negative infinity, the far left edge of the x-axis, this graph never goes above x equals 2, and it gets, or y equal to 2, and it gets microscopically close to y equal to 2. So the limit as x approaches negative infinity is also 2. I should add a little dashed line for your number 9, because it might not be obvious. So you'll notice that my graph in number 9 is microscopically, barely, you might not even be able to see it, but is microscopically above the x-axis. So the, that's not the best graph ever, but I guess it's good enough. So this graph, if I put a dashed line, that dashed line is going to go through 0 on the y-axis. And if I extend the graph out, going in both directions, that would be the proper extension of my graph. So this graph is going to stay just on this side microscopically above the x-axis, and once I cross the y-axis, it's going to stay microscopically below the y-axis. So your limits are going to be the y-coordinate of the y-axis. Hopefully you can get that. I won't spoil it by giving you the answer. The next few problems, the graphs don't flatten out. They either get real high or real low when we move from one side of when we move towards the infinities. For question A, it wants me to take this graph, and this graph would extend down like this forever. And so as I get further and further down, or further out on this graph, as I get closer to x equals infinity, the graph doesn't flatten out at all. When the graph doesn't flatten out at all, we say the limit as x goes to infinity doesn't exist. Some books would say the limit equals negative infinity, but I don't think that's really necessary. I think the limit doesn't exist if the graph doesn't flatten out. Similarly, if I looked at what happens to the graph as it moves out on the other side also doesn't flatten out. And when a graph doesn't flatten out, we say the limit doesn't exist. So the limit as we go to the far right edge of the graph or to the far left edge of the graph, because neither edge flattens out, we say the limits don't exist. That should be a heck of a lot like your problem 11, and possibly a bit like your problem 13. So pause the video, try to do number 11. If you could do 13 without my explanation of 14, that would be awesome. All right, so for problem 14, I'm supposed to extend the right-hand graph part of the graph and I extend it to the far edge of the x-axis. Because it doesn't flatten out, we say the limit as x goes to positive infinity does not exist. Similarly, if I do the left-hand part of the graph, which goes towards negative infinity, it doesn't flatten out, so we say that limit doesn't exist again. Hopefully that inspires you to do problem 13. All right, so I'm going to pause the video. I'm going to make this a two-part section. And in the next video, I'll pick up doing problems 15 through 21, and I'll try to, because that's already 39 minutes, and that's a good portion of video.